Hello everyone. Today we will discuss question 1, question 1 from the May-June 2025 Probability and Statistics 2 paper, A-Levels 970963, May-June 2025. I will be discussing the solutions, so we'll start with question 1. Question 1 is 8 marks. Alright, so question 1, let's just go through the question. At a certain shop, customers arrive independently and randomly at a constant average rate of 23.4 per hour. Find the probability that in a randomly chosen 1 minute period, at least 2 customers arrive. Alright, so for this particular question, what you have to find is the probability, and so our answer will be in the form of a probability. However, what's more important here is that we need to be able to decide which probability distribution to use. Right? So how do we know? We have to identify it, right? So how do I identify which probability distribution to use? So we look at whether or not the random variable is discrete or continuous, and that's the first thing. So here we know that the random variable would be discrete because it's about the number of customers. All right, so that narrows it down to Poisson or binomial, right? Poisson or binomial or geometric at this point, right? So now next, right? Our discrete random variable is described in an average value or a mean value, right? We describe the random variable using a mean value or an average value or an average rate. So whenever this is the keyword here, right, average or mean, right, that means, right, it's probably going to be Poisson. And to further reinforce this decision, right, the description of the average value of the random variable is described within a certain time or space interval. In this case, it is described using a time interval per hour. So first criteria, right? Discrete random variable, number of customers, described as an average within a time interval. So this means this is going to be Poisson. All right, so we're going to use Poisson distribution. So we have decided, right? All the other types of distribution do not have this detail or this criteria. All right, so we know we're going to use Poisson distribution. Now, here it says find the probability for a 1 minute period. Okay, we have our average rate is 23.4 per hour. Now, because the customers arrive independently and randomly, that means any chunk of this hour, right, will also be independent and random. And so as long as you choose any random chunk. So the chunk that we need is 1 minute. So what do? We have an average rate per hour. So to change it to an average rate per minute, we have to take the average rate here and divide it by 60 for chunks of 1 minute. So the lambda for Poisson distribution in this case would be 23.4 divided by 60, and we get 0.39. And this is nice and small. Remember, Poisson distribution is suitable for small values of lambda, not big values like 23.4. Okay, so 0.39, nice and small, suitable for our Poisson distribution. All right, so let's describe our Poisson distribution, right? X, let's name our random variable as X. Let it be the number of customers arriving at the shop, right, in a 1 minute period. Okay, so we'll say that X is Poisson distributed with lambda equal to 0.39, right? So now that we have set this up, now we can go ahead and answer the question, right? So we want at least 2 customers arrive. So that means we want to find the probability that at least 2 customers arrive. That means it's probability X larger than or equal to 2. Now the thing about this is that there is no upper limit to this, right? that means it's 2, 3, 4, 5, 6 or more, etc. To infinity. So we do not want to have or to calculate an infinite sum in this case, right? So what we can do is we can limit it by making it the by considering the complement. So so probability x larger than or equal to 2 is equal to 1 minus the complement of this, which is the probability x less than or equal to 1. And this is because there's a lower bound actually for this one, and that is because x is the number of customers, x can only be countable values, right, which is 0, 1, 2, 3, etc., etc. So we know that this is represented, probability x less than or equal to 1 is represented just by probability x equals 0 and probability x equals 1. So we then apply the Poisson probability formula for those individual values when x equals 0 and when x equals 1. You can find the formula if you can't memorize it, or if you don't memorize it, you can find the formula in the MF19. Just apply it carefully. Okay, so e to the power of negative lambda plus lambda e to the power of negative lambda. So this value here is for x equals 0 and this value here is for x equals 1. Okay, just carefully put brackets if you need to. Carefully evaluate this, right, and you will get this value 0.05889, and it goes on, right? And because we only want our answer to be in 3 significant figures, you can then write your final answer as 0.0589. Okay, all right, now let's move on to the next part of the question. Now the random variable x denotes the number of customers who arrive in a randomly chosen 1 hour period. So we're back to 1 hour, right? Just now the problem was for 1 minute, so now we're back to 1 hour. So we're going to use the same lambda which is 23.4 from the beginning. Here it says state a suitable approximating distribution for x giving the values of any parameters. Now why do we need an approximating distribution for x? Now when the lambda for a Poisson distribution is big, right, then it's better to use the approximating distribution, okay, for practical purposes. So since lambda is big, right, and we can see lambda is 23.4, what constitutes big for a lambda? For A levels, the standard is if your lambda value is larger than 15, then it's too big. It's big enough, basically, right? It's big enough such that we can use an approximating distribution. Now, if lambda is big enough, right, the approximating distribution that we can use is the normal distribution. So for normal distribution, you need 2 parameters, that is the mean and the standard deviation, or variance actually, right? So mean and variance. Now for a Poisson distribution, the main feature of a Poisson distribution is that the mean and the variance are equal. So our mean that we're going to use would be the lambda, which is 23.4, and the variance that we're going to use is going to also be the same as the mean, which is 23.4. So we can say that an appropriate approximating distribution for x would be the normal distribution, and the value of the parameters, right, would be the mean 23.4 and the variance 23.4. So this is our approximating distribution. All right, so now next they say use your approximating distribution to find the probability that x is between 20 and 30. Notice that 20 and 30 here are not included, okay, non-inclusive here, exclusive basically. All right, so this is the discrete random variable. X is a discrete random variable, so this will matter actually, okay. All right, we can since we're using normal distribution, we can then convert this to a problem using the standard normal distribution, using a standard normal variable z, okay, or z. So we have to apply the transformation. Now it would be our limit value minus, right, the mean divided by the standard deviation. So please remember 23.4 here is our variance, so we have to square root to get the standard deviation. Now notice here that I didn't write 20 here, I wrote 20.5. What is this? This is called the continuity correction. Okay, continuity correction. Why do we have to apply continuity correction? We have to apply continuity correction because we use a continuous probability distribution to approximate for the probability distribution of a discrete random variable. So when you have a discrete random variable and you approximate using a continuous random variable, you have to do the continuity correction. So how do we choose? Right here in this case, I added 20 plus 0.5, right? I added 0.5 to the 20. So how do we know whether we have to subtract or add 20.5? Okay, so what you have to do is you think about what we want here, right? What we want to be included. Usually what we do is we will have z here to be inclusive. So less than or equal, that means we want this limit to also be included in the probability. So if we use 19.5, for example, if you decide to subtract 0.5 here, if you use 19.5, that means 20 will be included in the limits. But here we don't want 20 to be included. So that means instead of subtracting 0.5, we should add 0.5 to 20. That way, z value will start, the limit will start at 20.5, causing 20 to be excluded as what the problem requires. And so you have to consider the same situation as well with the upper limit here, right? Should I add or subtract 0.5? Here you can see that 30 must be excluded. So we want a value that is a little bit less than 30. So we'll subtract 0.5 from 30 and we'll get 29.5. So this is called continuity correction. Okay, and it's usually worth 1 mark, right? If you perform the continuity correction correctly, there's always 1 mark allocated for it. Okay, so make sure you don't forget to perform the continuity correction. All right, so just evaluate these using a calculator and you'll get this. This is already z or z, standard normal distribution. Okay, so that and notice that the lower limit here of z is a negative number and the upper limit of z is a positive number. So whenever you're asked to find the probability that z lies between a negative and a positive value, you can always use the phi of the positive version of the lower value of z plus the phi of the upper value or the higher value of z in the probability, and then subtract 1. Okay, so this is the shortcut here. There are countless explanations online where they explain why this is the case. If you want, you can go and search for those. However, I will just proceed with the solution here, assuming that you guys know why this is the case. All right, so then use your MF19, the standard normal distribution table in your MF19, and find the probability for phi of 0.6 and phi of 1.261. All right, and you do that, right? Okay, these are the individual values here from the MF19, and then minus 1. Okay, so just evaluate this and you'll get 0.6221, and if you write that in 3 significant figures, it will be 0.622. All right, and that will be our probability, the probability that x is in between 20 and 30. And if you do get this value, you have done a good job.